All right, let's go back to this because we need to learn some rules for how you distribute negation, conjunction, so forth and so on. They're rules that are very much like De Morgan's rules for sets that apply in logic as well. In fact, they're called De Morgan's rules for logic. Okay, how do I combine the ands and the ors and the nots, right? I need to know how I do algebra with this stuff. Okay, let's look at some general rules. So what would not P or Q be equal to? P or Q is true if either or both is true, right? Okay, it's false only if both are false. So if I want to negate that, okay, so if I want to negate it, I have something that is true when both P and Q are false, and otherwise it's false. Okay, so this is not P and not Q. Okay, what about not P and Q? Okay, so this is true only when they're both true. Otherwise, it's false. So the negation is going to be false when they're both true, and true if either of them is false. Okay, so that looks like not P or not Q, right? And there's sort of parens around this, except that negation takes precedence over these other operations. So we don't need to do that. Yes?
Can you explain the logic? I know that because I know the logic now, but like I don't understand.
Okay, well, so we can just work it out. So where's it come? Well, we can just work it out, all right, to show that these two things really are logically equivalent. So let's go over what piece of board should I use? Well, I mean, it's really, so what does the truth table look like? So if we have P, Q, P or Q, not P or Q. True, 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 false, false, true, false, false. P or Q, we've got true, 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 false. This is false, 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 true. Yep. And then we look at what this is. Not P and not Q. What does its truth table look like? I didn't save enough room to write it here. Let me try to. Okay, so if P is false, so not P and not Q. So not P in this row, not P is false, not Q is false, false and false is false. Yep. Okay. In this row, P is true, so not P is false. True, so we have false and true, which is false. Okay, here we've got true and false, which is false. And in the last row, we have true and true, which is true. So it just has the same truth table. They just are equal. I mean, that's what they're logically equivalent statements. Okay, and this is one of the 16 possible truth tables. There are many other things that have this truth table, because you can continue to combine P and Q with and, or, and not, as long as you like. And it will whatever you get is going to evaluate to one of the 16 truth tables for two things. If you had three things, there'd be more of them. Before we go on, how many truth tables are there if you had three variables, P, Q, and R, you were combining?
81.
Bigger number, something. Okay. So how many rows would there be in the table?
Rows?
How many rows would there be in the table if we had P, Q, and R? We have all combinations of true and false for each of two variables, right? So there's two truth values, right? We've got two truth values for P. For each of those two truth values for P, we have two truth values for Q. For each of those, we have two truth values for R. It's 2 times 2 times 2, right? It's fundamental rule of counting. It's 2 cubed. Okay? So there's 2 cubed rows in the truth table for something with P, Q, and R. For each of those rows in the truth table, there's 2 possible values. It could evaluate to true or it could evaluate to false. So it's 2 to the power 2 cubed. Okay? So the number of truth tables with P, Q, and R would be 2 to the 2 cubed possible truth tables. And in general, if we had k variables, it would be 2 to the 2 to the k possible truth tables. Okay. Some of them are really simple. All true, all false, etc. Some of them are more complicated.